Hello, everyone. This is Huck. Welcome to ICASSP 2022. So this is the third part of the tutorial content neural network for speech and language processing. So, all right. So, yeah, see you on Monday. And in the third part of this tutorial, I will talk about the application for content-structured learning for speech and language processing. And it is Chao-Han Huck from Georgia Tech. And it is a joint tutorial with Dr. Samuel Chen and Junqi. Right, so in this talk, so first we'll have the background of quantum computing and machine learning and some examples of quantum advantage. And we will later have the quantum machine learning to representation learning. So we'll talk about from variational on server to quantum circuit learning. And then finally, we'll look at some hybrid classic quantum machine learning solution. For example, quantum circuit learning and its application for speech and language processing. And finally, will be some question answer, and we'll see you online. So let's look at the first part, the background. Right, so before we talk about what is quantum machine learning, so we should look at what kind of data and algorithm we are looking today. For example, when we try to design algorithm, in most of the quantum physics and the original pure quantum algorithm, those data and algorithm that could be quantum. For example, we have the gravity wave, and we use some Schrodinger equation to serve those kind of Hamilton system. And for most of our machine learning, for example, if we work on a speech processing problem, so we have a classic data like human speech, and then we use classic algorithm like HMN or deep neural network to resolve those kind of problems. But meanwhile, we also can have some quantum data, but we use some classic algorithm to learn better about those kind of data. For example, when we reconstruct the black hole, or when we use some pattern recognition technique to learn better about the physics measurement. But for today, we'll also look at if there is some classic data, for example, speech or language data, can we use some quantum or quantum-inspired algorithm to learn those kind of data and its representation better? Oh, but meanwhile, we also have some pros and cons about using those kind of quantum algorithm. For example, the most promising like advantage could be quantum speed up. Like by using some quantum algorithm, the sample capacity or time capacity can be faster. And then we can have larger representation space. We can encoding this phase and amplitude. And then we can have memory and model capacity advantage. But as a hardware solution, quantum computing will face some challenge from error correction, from its entanglement or coherent from its hardware constraint. So if you have like not a big picture about what quantum or those kind of space we are processing right now, you can think we have a ball. For example, we have a ball vector, and the vector will coming from the a space which containing the phase and amplitude information, and we have the classic x and y, but we also have the qubit. So for more information, you can refer to the first part of this tutorial. But when we talk about quantum speedup, we can look at this paper, Quantum Machine Learning, published in Nature in 2017. So there's different classic machine learning approaches like Bayesian inference, online perception, discrete fitting, classic Boltzmann machine, quantum Boltzmann machine, quantum PCA or quantum supervector machine, and quantum reinforced learning. So as a algorithm, we have this speed up. For example, we can have like log n and like sorry square n and the log n like speed up compared to its classic computation. And then we can have this amplitude implication for the speed up, for the quadratic speed up and the HHL algorithm. So this is a classic quantum algorithm for resolving a linear system. For example, we want to find this inverse matrix and quantum random access memory if we want to have a pure quantum computing solution. So those kind of example we can think of, if we can have a pure quantum data and a pure quantum algorithm, the speed out can be really obvious. But these things will be under some limitation from this both hardware and the algorithm design. For example, if we have a parameterized variational quantum ion server, so first we can have a problem like a Fermionian problem like a Hamilton system. We're trying to describe a molecular architecture or a multi-body physics problem by using a Hamilton system to describe this property we want to describe. And then we can have a classic cost function, for example, the traveling salesman and the sorted parts we want to reserve. So we can reforming this kind of nature observation to a qubit Hamilton system. So here is some kind of encoding and a gate. And in the computational progress, so we had a classic training objective. For example, we calculate NH, we can adjust the parameter to optimize this Hamilton. And finally, we do the measurement and we find a good parameter can reserve this ion server. But you may ask, saying we under those kind of challenge and limitation, why we still want to study quantum machine learning or quantum computing with classic data at this moment. So here is a picture from a paper published in 2016. So this paper foresee this early delivery of this quantum hardware and quantum software converge. For example, in the early deliverable, we can think about this quantum accelerated idea and those symbiotic solution for this quantum accelerator. And finally, we can implement this quantum accelerator based on different qubit and different develop of the quantum machine. In the early deliverable, we could only have these assets of this quantum computing architecture by some cloud computing technique or some hybrid system, which means part of the computation architecture that quantum part of still depends on this classic training objective and like the gradient-based optimization technique. But we still can access part of this quantum advantage by designing the hybrid system. So this foresee is possible currently at this stage. And we indeed to see this hardware and there is like pop up and we have more near-term algorithm and near-term solution gradually come over different data and gradually come different domain. One of example is last year, our group just find out we can use a random quantum convolution to do feature extraction for speech processing. So here is another example of recent development of quantum hardware. So in 1998, IBM Octafer Berkeley and Stanford, MIT, they find out we can have a quantum computer with 2 qubits. But for now, we can have a quantum machine, and everybody can connect to a quantum machine from IBM with 4 qubits for free. And if you have this collaboration, or you buy this business solution with IBM or the other provider like Google or Rigetti, we can have quantum machine, a real quantum machine over like 50 qubits. And by the roadmap, like 2022 is halfway through now, but we can have more qubit based on this development. So you can look at this kind of exponential increase based on the scale of the quantum machine. Meanwhile, also have some solution like the tensor simulation to reserve to simulate a quantum processing unit, like the TPU secret released from Google, like the Google last year. So I mean, like we can witness this processing, like the early development of the neural network is really based on, it certainly get empowered by the GPU, but we can witness this processing is ongoing. But from the classic world, we will have some challenge like the coherent issues. But before we really get into this error correction and to have a really empirical and usable large-scale quantum machine, we can still do some like prototyping of or some early development of this quantum algorithm, like these near-term intermediate scale quantum devices. That means this device is still enough to barely suffer from this error correction, but we can still do some quantum computing based on these devices. Another solution is from the Google AI block. Sorry, should be a perspective. So we have this limit error correction rate, and we have the number of qubits. Like if we only have a few qubits, we couldn't do some application for the quantum machine learning or have this speed off based on this sample space. But before we really have a user for error correct quantum computing, we can still do some near-term application. That means we use part of this qubit for the encoding or some quantum simulation, and then we still trying to make our classic data and classic model better. So here is something we currently routine right now. So there is some other discussion about the quantum machine learning because it's apparently is a new direction. So is the quantum advantage the right goal for quantum machine learning, which is a new paper just published 2 months ago by Maria Shio and Nansen. So they asked like so at this moment, so we don't have a fully functionable large-scale quantum machine, but the searching of a quantum perception, like a universal approximation based on some quantum encoding is important. And the link between quantum circuit learning and the kernel learning theory, are they the same or not the same? Where is the similarity? Because we know quantum circuits is basically tensor network. And then finally, the quantum software for machine learning application. So can we really build up some useful application for machine learning and to process those data? So here is this tutorial, at least for my part, is focused about. But I want to highlight the foundation of the quantum machine learning and the kernel learning. They are also really hot topic right now. So you can look at in the kernel methods, we have the data space and the feature space, and we use a kernel to do this, the conversion. But for quantum computing, we have the input space and the quantum Hilbert space. And we access this like space by measurement, but we can think of this tensor network is kind of the kernel learning from some researchers' perspective. All right, so here is some take-home message of this session 1. So with this fast development of quantum hardware, understanding and designing new quantum or quantum-inspired algorithm is an emerging issue. So if something happened right away, and we under this background of the quantum computers still scale out every year. And then the near-term quantum algorithm could be the current goal running on near-term quantum computers. For example, even we have a free access, we can access a quantum computer with 4 qubits and with some advantage. So we can see this simple advantage, but we'll have more concrete example later. And then quantum machine learning have different goals from its theory to its application. So it depends on what kind of background you want to look at. Okay, so let's come to the second part of this tutorial. So quantum machine learning to computational learning. So we are looking at some classic algorithm before quantum circuit learning, and then we will talk about why we especially talk about quantum circuit learning this time. All right, so we know there's different variational quantum algorithms. Variational means like we have a parameter and we use some parameter or some approximation to update our quantum algorithm. For example, we have a tensor network, which is the quantum gate here. And then we have a classic optimizer, for example, a gradient or different kind of black box optimization technique like evolution or gradient-free algorithm or Bayesian approximation. So for variational quantum ion servers, like we can resolving some classic problem like exponential wall challenge based on this dimension of the Hamilton system. So by using some quantum machine and these quantum ion servers, like the problem scale can be the original some problem we couldn't deal with, but we can scale down this problem and to come over this exponential wall challenge, which is classic in a lot of physical or the chemical like application. And then some classic algorithm like quantum approximation optimization problem like QAOA. And then there'll be the parameterized variational quantum circuit learning is one of our focus today. So basically you can think of, we have some parameter, and then no matter we put this parameter a weight in our quantum system or a classic data encoding into a quantum data and use a quantum circuit system to resolve this classic data. But you can just think of it as a quantum system as a black box, but we will still use some classic algorithm to compute this loss function and then use some parameter update technique to optimize our quantum system. So you can think of these things as a Hamilton system after this encoding, or originally it's a quantum data. And then we're trying to optimize these things based on some gate processing. So here is a good example from the paper by the quantum circuit learning published in 2019. So so we have the classic counterpart, for example, similar annealing, echo state network or neural network. And we have a hybrid algorithm, for example, the VQE, the QAOA, QRC, or quantum circuit learning. So they are coming from different perspectives. For example, for VQE or QAOA, so we're trying to minimize the output of the quantum circuit. So here is something we get out from the quantum circuit, and then we use this theta to resolve this Hamilton system. But for echo state network or QRC, we're trying to tune the weight, which is the W here, and then we're trying to find this F, which is approximate this BX out of from our quantum circuit. But for the parameter of this unitary gate, they are fixed for the second part. But for third part, which is the quantum circuit learning we look at today, some people also call it quantum neural network because it's a black box system. So we're trying to update this circuit parameter in order to have a teacher model of the F originally, and then to approximate this output of the gates from a loss function. So if you do this neural network-based optimization, you can think of this loss is very similar to how we train this neural network. But meanwhile, I have to say we couldn't do backpropagation on this quantum circuit learning. So some people discuss whether this computing process is NP hard problem or not. But if we scale down the problem, or if we just only use the circuit learning to a part of this application, the computation while still feasible, and we also have some other solution to deal with this quantum circuit learning. So for detail on how we can design hybrid model beyond speech and language processing, you can also look at Dr. Yanqi Chen's tutorial as a part one of this tutorial. All right, so there's another discussion whether the quantum circuit is pure tensor network, so they only do this linear mapping. But where is some non-linearity here with the quantum circuit learning? So there's, for example, Dr. Maria show like she talked about supervised quantum machine learning model kernel masses, but there's some recent discussion about quantum machine learning beyond kernel masses. I have to say, as our discussion on about whether our kernel learning is equivalent to quantum circuit learning, there's a different solution or different design, both empirically and fundamentally. For example, if we only do this encoding or the quantum measurement, these things can consider as a kernel learning, but we also have this data uploading processing by circuit, so we can add some nonlinearity here. So this is a paper from this. It's a figure from the second paper. So here we can have the exact mapping, and then we use this quantum solution to reduce this temporal capacity. But if we have a re-uploading models, we can add in some linearity here to deal with this non-linearity from the data. Another paper is from Junqi. So we can now we can do some theoretical error performance analysis for variational quantum circuit. For example, we can use a tensor network, just another tensor network, not identically equivalent to quantum variational quantum circuit because they have some activation to add this nonlinearity, and then we're feeding this output of the tensor network to a variational circuit, and then we have this nonlinearity, and we can do this pattern classification. So yeah, so now we know like we have this quantum circuit, and quantum circuit can be updating like we train a neural network. Although we couldn't do backpropagation, but we can do this parameter shifting, like how we train this black box model. But I also want to highlight there is some quantum computing and natural language processing before like the variational quantum circuit. So basically they are define a quantum language model based on some density functions. For example, Tor quantum language model and the novel task classifier based on quantum computation, and how we modeling this quantum language model and with some distribution-based hypothesis. So one of the classic example is we can model a quantum, we can use some quantum modeling to model the terms of our language. For example, if we can compound these terms as a density matrix without having expanding the space, we can encode in both information we train the model. That means if we have a sentence matrix, we can do some auto production and then to formulate these things a density matrix. And then we can use some quantum mechanics to simulate this density matrix in a large representation space. So we can use this vector finally for the different tasks. For their paper, they use for question answering to train an end-to-end model. But here is the general representation from this density matrix. Another perspective is some advantage of using quantum NLP. One example is under this dimension and Hilbert space with p-dimension vector, so which published in ACL in 2013. So we can find out if we directly use a QLM, so dimension is much smaller, but we can have a lower capacity. So here is not focusing on the gradient propagation training and learning, but we also have some pros and cons to avoid using hybrid classic content model, because right now, if we have a neural network based model, we basically have to do this backpropagation. But if we couldn't backpropagate all the model directly, the computation time could be a problem. But this early work we can look at, even we don't do this end-to-end training, we still can have some advantage based on this parameter capacity or the performance. Another recent work I want to talk about is quantum-inspired multi-layer perception. So in a really recent work from CBPR 2022, so they simulate this input with the amplitude phase. And then we record encoding this real part and the imagined part as a wave function is how we processing this data in the quantum mechanics. Since we can learn both amplitude and phase from our data, so we can finally have information as a vector, and then by defining this information, so they find out the performance can come over with swing transformer, which is another really promising result. So different data coming from different input, we can simulate this as a different density function in a wave function. So if you are interested, we can find out this paper. So finally, we have these patches, and then we can use how we compute this MLP to do this transformer-based learning. All right, so now we know there's different alternative we do this quantum computing, and we now beyond this quantum circuit learning, there's some other solution. But is there any since these tutorials mainly talk about quantum circuit learning, so why we need quantum circuit learning, and how could we really train a hybrid classic quantum machine learning model, and could we use it for speech and language processing? So we know the hypothesis saying if we do some quantum mapping, we can have more feature representation from both a vector and this shape. But the problem is this end-to-end process is often take a lot of time because we couldn't do backpropagation. For example, if we have an input, we do the convolution, how we do this convolution, we're doing in the classic neural network. We can replace each component with a quantum circuit. For example, some circuit is trying to do this pooling, downsampling this information, and we can do the convolution, we have a side window go over each input information, and then finally we have fully connect based on the circuit design, and finally we do the output with the measurement. That means if we parameterize each component, we can somehow to mimic those components we do in the neural network, but meanwhile we have more information because we have the phase data and we can encode this data in a large space. And one of the example is quantum enhanced transformer is based on a universal encoder. So one of the sample encoder is from our previous paper with Dr. Samuel Yanqi Chen. So we can find out, we can simplify the quantum circuit but as a universal encoder, but have some trainable information. For example, these gates represent a general single qubit. So for example, it's qubit 1, qubit 2, qubit 3, qubit 4. So this unitary gate with some three trainable parameters. So you can think is how we rotate this vector and then to learn this vector doing this end-to-end training. So by having those basic components, we can define different quantum perception, as we say at the beginning, but we can use this quantum encoder like dense encoder, which used in the neural network to design advanced or trying to mimic the advanced machine learning models like transformer, LSTM, and those kind of solutions. So I want to highlight a paper from Ricardo. It's the dawn of the quantum language processing. So in their work, they designed some quantum LSTM and multi-hit quantum intention. So you can think of, they have a quantum circuit based on this angle embedding, and the entanglement layer is the previous slide is one entanglement layer as an example. And then we can use this like Keras layer as a dense layer to have the key, the Curie key and value is how we do this transformer-based computation. But there is some problem if we like to quantize all the deep learning model with this circuit, because even the classic to quantum encoding process often takes a lot of time. For example, if we have a means with 60,000 samples, if we only do this CPU-based simulation, for example, I want to do some simulation before I put this data to a real quantum cloud solution or quantum computer. So we want to see our code is functionable or not. But even this encoding process takes up time. Usually, one experiment takes 20 to 30 days. And second problem is, since you want to parameterize training this model, they are basically black box model, and we couldn't do backpropagation. So if we use gradient shifting to train this model, they will take even longer by a single CPU. So that means it is near-term era, like right now, could we have some other options, like skip the training time, but only use the encoding property from this quantum circuit. So one, I would say is a good idea is like empower image recognition with quantum circuit by Henderson, M. Henderson, and the researcher. So they're trying to like use the random quantum circuit for this convolution. For example, as the early stage of the neural network, we'll also find out if we have a random neural network, the pattern or the feature we like extract can already containing some useful information. But here, if we have input data, we can design quantum circuit with only few qubits. For example, here we only have 4 qubits. So this is like how we can really do with the quantum computer. But by these 4 qubits, we can scanning those kind of inputs. For example, each input we scan with this qubit, and then we can have a projection in the quantum space. And then finally, we do this encoding to have this information as back to the real space. And then we can put this information by this random encoding to pooling and the convolution again. And finally, the last part is a classic model. So there is some good property, because since we use a random quantum circuit, which means the parameter here is random initialized. So we don't do the model training, but we have the encoding, so the computation will not take such long. But their finding is quite interesting. For example, by different size of the filter, even they use a random circuit, they can have good performance for means classification. Like no matter it's random or not, like they can have really competitive performance. So another work is from last year with Professor Qinghui Li at Georgia Tech. So we are thinking, if we really have limited resource from this quantum computer, what kind of the problem we can resolve. For classic data, the input is bit, but we use DNN or chain to learn this data and the output speed. The property is compare really easy to implement, and everybody can implement with a computer. But for a pure quantum approach, the input is qubit. The learning model can be some parameterized circuit or the other model we mentioned above previously. But the output is qubit. That means we don't really need this qubit at this moment as a computer scientist. But if we have a hyper CQ, like mean hyperclassic quantum algorithm, the input could bit. But if we replace part of the computing process with a quantum algorithm, we can somehow access this parameter capacity advantage and the representation mapping advantage. And finally, we can access this quantum advantage by replacing part of computation architecture by variable learning or the other hybrid or heterogeneous computation system. That means by having those kind of isolation architecture, we can somehow do this data protection and to be suitable with the new data regulation, like the general data protection regulation and the California Customer Privacy Act. So that means we can have some good solution even with the limits access on the quantum computer. For example, if we have a random quantum convolution like the previous paper, so we can let the local user to upload a speech, and then a server or cloud API that will extract the mail feature, but then we use the random feature structure to pick out the feature. And finally, when we have this feature, we can do this deep learning based training and prediction. For example, the speech comment prediction or the ASR prediction by replacing different loss functions like the CTC or cosine. All right, so we can find out in each channel, even by this random convolution, the content encode feature actually containing different information. For example, channel 1 learning the shape and then manifold of our Mail spectrogram, the power here, and channel 2 learning some low frequency feature, and channel 3 learns some high frequency feature, and channel 4 learns some lower band information. And if we look at the encoded feature from the Mail spectrogram over different convolution encoder, for example, neural convolution like the B here, quantum convolution like the C here, and different kernel quantum convolution, we find out if we select properly with this quantum random quantum convolution, they can have similar information containing with the trainable neural convolution kernel. And we find out if we select properly with this 2x2 quantum kernel, the performance have slightly improved with a really well-tuned baseline neural model, which is the SOTA model back to 2021. But when the kernel size becomes too big, they have a big performance drop. So how to tune and design better convolution model or trying to stabilize this computation process is still an open problem. And finally, if we look at what actually this hybrid model learn by class activation mapping, we can look at the heat map over the feature. And if we look at the B here, the convolution plus RN, the convolution encode feature actually mapping back to this original Mail spectrogram. We can see there's a lot of detail aligned to the original spectrogram by this class activation mapping. Finally, from another perspective, saying we, in this case, slide number 33, if we don't use trainable, if we don't use a random convolution encoder, saying there's a trainable convolution kernel, we find out the convergence speed with this quantum convolution, they actually converge faster. For example, if we look at the blue line here, they actually take less than 10 apple to attain the accuracy over 90%, which because we have, which could be due to because we're using fewer model parameters, so the convergence speed become faster because there's a smaller searching space have to search. So after we look at this, the promising attempt on the speed processing, we in this year we also try to do this convolution, random convolution or trainable convolution on the task classification. So, but this time we still use a limit qubit quantum computer, saying by processing the embedding from a pre-trained language model. So saying we have a BERT model over here, which is a pre-trained model. So after this BERT model, we have a processor called the quantum temporal convolution, which is a QCT here. So QCT will learn this temporal information over a side channel, one dimension, and we'll go over a global max Boolean and have this dense projection and finally do output prediction. So this work with collaborate with Professor Yu Cao from Academia Sinica at Taiwan. So basically you can think of there's a ton of order of input sequence that are embedding here. And then the proposed temporal convolution just go over this embedding by the token size, like saying what kind of window we want to look at, and then compute a feature after dot product. And finally, we got information by this temporal convolution. Another perspective, not really coming from the representation learning, is to use variational circuit as a symbolic computing. So this is a paper from Cambridge Quantum Computing, Cambridge CQC. So they use variational quantum circuit to model the grammar architecture, saying if we have a meaning about such a noun and verb, can we also try to compute this grammar structure by variational circuit? So here we give examples saying we have Alice hates Bob, and then we modeling Alex this noun with some parameter, hate with some parameter with some variable, and Bob with some other variable. We want to learn this symbolic information. The meaning of a noun is one qubit state, which is a Hamilton information here. And then we can modeling this grammar architecture with some variable alpha and gamma here, and verbose variable and Bob's variable. And then by different information, like the saying we have a black hat. So the central information, the objective is hat, with the black information. So finally, we can use a gate to construct this grammar concept. So we have the gate here, and then we have the black here. So interestingly, this alternative attempt also achieve good quantum advantage. So by saying a compositional language circuit. Compared with the classic algorithm, the quantum compositional language circuit only takes 33 qubits, where the classic model will take billions qubits to compute a verb as a kind of noun. So this showing some capacity advantage to dealing with a really large grammar information, which could not handle by classic computer. And then their work also showing some interesting example about copy, merge, and delete to model this symbolic information by variational circuit. And this grammar architecture is actually trainable by updating this parameter in the gate. So you can think of, we use gate to simulate those kind of information. Another approaches I want to highlight is also published in ICASSP this year by Norman DePort and Mr. H. Wang. So their idea is to match point set with quantum circuit learning. So this is a computer vision based approaches. So saying a classic problem about optimal transport. So we have a certain kind of pair of the points, and we have another pair of points want to match in those points. So we can use the kernel collection laws to do this point matching. So for more complex points like a geometry, architecture, or point count, we can use this kernel correlation to do this point matching. But can we also model in this kernel correlation with the quantum circuit? That means we require least qubit and to do this the servers. So their idea is modeling this optimal transport function like M and D by the quantum circuit. And their finding is by using really empirical near-term quantum machine like 4 qubit or 6 qubit, we can actually do this point transport for computer vision-based application. As far as we know, this sequence modeling can be also work well for speech enhancement or autoregressive language model. So I believe this work can have good impact for speech and language modeling community also. So you can also find out their work in ICASSP this year. Finally, we want to highlight the computational power of data. So the computational capacity for quantum and classic data can be both get help with the quantum machine. For example, we can simulating quantum system are classified as bounded polynomial time, which is here. And those problems are easily solved on quantum computer called bounded probability polynomial problem, which is here. But actually, there's an overlap here. Is we're trying to see the means problem. But meanwhile, there is some problem like the traveling salesman can easily resolve a classic computer or the exponential world issues to work with more a larger scale problem with this quantum machine to learn the phase of the context value. But there is an overlap here we want to discuss by their paper. So it's like they finally showed out based on this projection quantum kernel. Depends on different system size, the projection quantum kernel can perform better prediction accuracy compared to the best classical machine learning model, which is a really promising result. So yeah, so this is almost the end of the talk. So here are some conclusion for this third part of the tutorial. So I want to say both question accuracy and data are very selective at this moment for this near-term quantum era. This is how we scale down the problem and how we can look at there's some problem really need this quantum algorithm. But meanwhile, we can also design new algorithm for future, even the system is not ready for those this quantum circuit algorithm like the quantum transformer as an example. But when we have to use this hybrid classic quantum model for machine learning, we can also think of there's an opportunity from system perspective. Saying there's a large pre-trained model available, can we design a VQC-based hybrid model to isolate this model parameter and to encrypt those like data to avoiding parameter leakage is an open direction. And finally, in the preliminary survey or even more previous work, we find out there is some simple capacity advantage and also some representation learning advantage from both VQC learning or the density function or the weight function modeling. So like by having more like quantum hardware, we can access those like advantage by both real quantum machine simulation or tensor-based processor. So this is something just happened right now. Finally, I want to say this year we have a special section for the quantum machine learning for speech and language processing. There is a lot of fun paper there, the quantum LSTM, the point matching, and a lot of new papers showing up there. And you can find a special session on Sunday, just right before the tutorial, but you can look at the video. And I want to give my big acknowledgement to my collaborator, Junqi from Georgia Tech, Dr. Samuel Chen from Brookhaven National Lab, Professor Yu Chao from Academic Sinica, Dr. Pingyu Chen from IBM Research, Dr. Mingshu Xie from Foxconn Quantum, Professor Sabato Marco from Cole University of Anna, and Professor Qinghua Li from Georgia Tech. And feel free to contact me if you have any questions on the application part of this quantum machine learning. And we also want to give our big acknowledgement to those reference from both physics community and the machine learning community and the speech and acoustic modeling community. All right, so hope you enjoy ICASSP 2022 and see you both virtually and or by the Gator Town. Take care.